Today we're going to study a really important topic and process that can help us to solve any quadratic equation. Because so far all we've worked with are ones that can be factored, but there's way more quadratic equations that exist that can't be factored. And if that's true, how can we solve them, or can we solve them? Well, the answer is yeah, we have ways to do that, and it will help us after we go through today's lesson. So our prior knowledge today is remembering the difference of squares pattern, and then remembering how to factor a quadratic and also solve equations involving these two processes. And then just in general, the polynomial vocabulary we've been learning. So if any of those things you need to go back and look through your notes at or whatever, make sure that you go do that. We have a couple warm-ups today. It's a little longer than usual. And I want you to go ahead and do these yourself. Now these ones would be ones you try to factor and then use the ZPP for. And then these ones, if you notice, these all involve potentially a difference of squares, or maybe there's another way you could learn, or you could use to solve them. What I'd say is try to do A, B, and C yourself, and we'll probably do and talk about D, E, and F together ourselves. So please pause now and at least do A and B and C. Okay, so all right, I'm going to give you right away. If you tried to solve C by factoring, you probably figured out that it doesn't work. So I'll tell you that right now. Okay, but at least A and B you should have gotten solutions for those. Let's just remind ourselves. Well, remember, it might be easy for you to tell that 0 works for this one, but remember, if we factor it, and in this case, there's a common factor of x, so have x times x plus 12 equals 0. And remember, I can't do that for ones like this because there's not anything in common between all the terms, right? That's why we had to figure out a different way of solving ones like this one, okay? So ones like A are kind of the easiest ones. Is there anything in common between everything? And then we can try to pull that out first, and then it makes it easier to solve. And then here we can see either x equals 0, because if we do 0 times anything, we get 0, so that works. Or if I make negative 12, because that makes this piece 0, right? So 0 or negative 12. Now for B, we, again, would want to try to solve this by factoring if we can, and we should be able to. Let's see. I think this is going to be x plus 10 times x plus 2, I believe. 10 times 2 is 20, and then 10x plus 2x was going to give me 12x, so yes, that's correct. And then we have x equals negative 10 or negative 2. Those are my two solutions to that equation. And then last, well, you probably realized, and I already said it, that I'm not sure what to do with that equation. So for now, let's just leave that one, and we'll revisit it. Now, there's a process we've talked about for solving ones like this. Now, there's two things. This does involve a difference of squares. You can remember this is x squared minus 5 squared, and then know that this is x plus 5 times x minus 5. Okay, so that's a pattern to remember that's important, and make that equal 0, and you can say, oh, okay, so x equals negative 5 or positive 5, and those are my two solutions. But I do want to remind you that we could actually solve this one by backtracking. If I add 25, I get x squared equals 25, right? If I add 25 onto both sides. And then from there, I would want to do a square root on both sides. But remember, if I just square root 25, I get x equals only 5, right? But we know from this way that there's actually plus or minus 5 that works. But remember, actually, there are two numbers that you could square to get 25. So we need to make sure that when we're doing this way, we remember the plus or minus portion. Okay? So we can do the same thing for E and F. We could factor them, and we have learned where we could factor these. For example, don't get confused about this being kind of weird. Since this is something squared minus, and remember 9 is 3 squared, right? Then we get x plus 4 plus 3 times x plus 4 minus 3 equals 0. And then this gives me x plus 7, x plus 1, and therefore x equals negative 7 or negative 1. But I want to remind you guys of something. We could also have done something different. If x plus 4 squared minus 9 equals 0, we could have done x plus 4 squared, remember, backtracking. So this one actually can be done with backtracking, equals 9. Because if I did minus 9 at the end, then if I want to undo things, I could add 9 first. And then from there, I would, I guess I'm not following my right color scheme here, but that's okay. I could square root both sides, and then this would lead me to, and remember the square root and the squared undo each other, right? So it just gives me x plus 4 equals square root 9 is 3. But remember, it's plus or minus 3. And here's the cool thing. Since it's either positive 3 or negative 3, and we subtract 4 here, we're either going to get negative 7 or negative 1. So it still works out the same way. Now I'll be honest with you guys. I personally think it's a little more efficient or easier to like use backtracking because you're just like reversing the steps, you know? And that's something we are very comfortable with. So I would not expect that you need to use the factoring method for these ones. I would say that for ones like these, this is probably the easiest method to actually use. Now you might have noticed that for f, 10 is not a perfect square. So if I even tried to use factoring, how could I do that? Well, we'd actually end up using the square root still, square root of 10, which is not a nice number, but you could still leave it as the square root of 10. Now let's actually use just the second way to solve f together here. And again, this is just backtracking, right? So if I'm adding 4, then squaring, then subtracting 10, let's just undo all those steps. So I'm going to add 10, right? Because that's the last thing that was done. And then that's going to lead me to, I don't know, my colors are off. X plus 4 squared equals 10. And then square root, because that's the next thing I need to undo. And remember, I'm going to need a plus or minus. So I have x plus 4 equals plus or minus square root 10. Now, if you like, you can certainly make that into a decimal, and then you're going to get approximate answers, not exact answers. But for now, since we don't really care about the decimal, I'm just going to leave it like it is right here. And there's really one last step. We just need to subtract the 4 away. So this is kind of weird looking, I get it. But our solutions here are going to be x equals plus or minus square root 10 minus 4. And I know that seems really weird, but again, if you just think about the square root of 10, the square root of 10 is just a little bit more than 3, right? Because the square root of 9 is 3. So this is basically like saying maybe 3.1, plus or minus 3.1, and then minus 4. It's still going to give me 2 answers. Okay? So what we're going to look at in the patterns today are going to help us to deal with equations like this that don't have nice integer solutions, and like part C over here, because we saw that that one doesn't factor with integers, so how can we deal with it? And we're going to learn how to deal with ones like that. Dive straight into a few examples first to kind of show you what it is we're trying to get to. We're going to kind of start with the goal first, and then we're going to learn, well, how do I actually connect that together? So first, this is one you can do on your own. So I would again like you to pause right now and do number 1, and then we'll use our result here to solve number 2. Okay, let's check our work. Now remember, this is what we call normal form, right? Because it's all expanded and simplified. And this one we would probably need to work with and expand it and combine like terms to show that it equals that. So to show this identity is true, we're going to start by taking the left side. And remember, x plus 6 squared, you cannot just distribute the exponent. We have to actually multiply x plus 6 by himself. And then in the end, we're going to subtract 15, right? Well, if you multiply x plus 6 times x plus 6, this is nice because it's 6 and 6. So it's going to end up being 6x plus 6x, which is x squared plus 12x. And then 6 times 6 is going to give me my 36, right? And then in the end, I have that minus 15 there still, right? So this is my x plus 6 times x plus 6, then minus 15. So the good thing is here, 36 minus 15, these parentheses aren't necessary, it's just to help you remember that it's the same as that piece, right? So in the end here, it's just 36 minus 15 that we need to worry about, and we have x squared plus 12x, and that is 21. So I have shown that that is, in fact, an identity. And you'll learn that today the equations, well, what we're going to focus on with these kind of equations, and we're going to look at this, is how to bring it to becoming a perfect square. Because watch this. Now that we know that this is the same as that, let's go to our equation that we saw in part C for our last example. If we want to solve this equation, what we can do here is rewrite it. Now that we know it's the same as x plus 6 squared minus 15, then this equation is exactly the same as that equation because these are two equivalent polynomials, right? These expressions are just exactly the same as each other. And now I can just solve it by backtracking. So let's do that. My first step would be to undo by adding 15. And so I have x plus 6 squared equals 15. And then I have to undo the squared next. And then what I get here is x plus 6 equals, and remember we need that plus or minus because there are two roots, right, of 15, or of any number. Now we have one last step to go because we need to solve for x, right? So we're going to subtract 6, and I get x equals, technically speaking, we typically put this number first. So we could do plus or minus root 15 and then minus 6, but we often actually put this first. So I'll say negative 6 plus or minus root 15. And again, if you would like the exact, well, this is the exact. If you would like the approximate decimals for that, you can certainly do that in your calculator and get negative 6 plus root 15 and then negative 6 minus root 15. And in fact, let me grab my calculator real quick and do that. I meant to do this just to help you have a gauge for this. So if I do negative 6 plus root 15, it's about negative 2.18. Negative 2.18. And if I do negative 6 minus root 15, I get approximately negative 9.87. Okay, so these are really my solutions here. That's the best way or the most accurate way of expressing them. But if you want to know more like the number line and see where they actually fit there, then converting them to an approximate decimal is okay there. So our whole goal today, this is our goal today, is how do I know that this was the same as that? Because I kind of gave that to you, right? So our whole goal in this lesson today is going to be figuring out how to take something in normal form and write it in this form so I can solve it by backtracking, right? So let's put that together with each other right now as we dive into more technical details of how do I actually do this. Now let's talk about the actual title of today's lesson. Perfect square trinomials are really important to the process. Now the process that's important today is called completing the square. So a perfect square trinomial is a trinomial. Remember, that just means a polynomial with 1, 2, 3 terms in it when it's in normal form. With identical factors. Remember, identical factors just means, like in this case, x plus 6 squared is x plus 6 times itself, right? So when I say identical factors, we really just mean it's a perfect square. So x squared plus 12x plus 36 is a perfect square trinomial because it's the same as the perfect square of x plus 6. Okay? So that's why this is called a perfect square, because it is the result of taking x plus 6 and squaring it. Alright? So that's really important for our lesson today, because if you look back at our example we just had, we saw that x squared plus 12x plus 21 equals 0 is the same as x plus 6 all squared minus 15 equals 0. And this was way easier to deal with. We saw this wasn't factorable, so we couldn't do it that way. But if we put it this way, we could backtrack it. So completing the square happens to be the process of putting a quadratic into the form we can backtrack, like this. Okay? So now we're going to talk a little bit about completing the square and figuring out how can we actually figure out, that was a weird word choice, but talking about how we can actually figure out how to connect this guy and to know that he's the same as that. And at the end of this lesson, you should be very able to do so. Let's take a look deeper at completing the square. An important rule here, and really this rule is just like a side note to our factoring rule that we talked about before, our sum and product pattern from our last lesson, but it still is an important rule. So if I'm doing the perfect square of something, okay, so remember x plus b all squared means x plus b times x plus b, right? And if you expand that all out, you're going to get x squared plus bx plus another bx plus b squared. Well, if you have bx plus bx, b plus b is 2b, right? So let's look carefully here. Whatever this number was here for b, how does that relate to my result there and my result there? This coefficient is always 2b, which is double that, right? And then this constant at the end is always b squared, because it ended up being b times b. So you can take this square. And that can help us figure out how to convert from normal form to factored form if it's a perfect square. So this is the next thing I want you to do real quick, and then we're going to actually look at a nice visual way to understand this pattern as well. What's missing here, right? Go ahead and figure out what's missing there and what's missing here and here. Okay, let's take a look at your solutions. Well, since we know whatever there needs to be doubled to get this and squared to get this, luckily these work out to be the same thing. You should get 7. If you expand x plus 7 times x plus 7, you're going to get x squared plus 14x plus 49. How about x plus 4 all squared? Well, again, remember this is double, so this is 8, and then this here is the square, and 4 squared is 16, so that equals x squared plus 8x plus 16. Let's take a look now, as I promised, at a visual for this. We have a square, right? And remember, if we're talking about perfect square trinomials, we haven't quite gotten to this process yet, but then it's always like we're talking about x plus some number squared, right? So in this case, we could just call this, if this whole thing was just x, then of course, what's the area of that square? Oh, x times x, which is x squared. But we're kind of talking about this perfect square where I've split this. So let's say that's x, and let's say this much is b. So we're going to call this x plus b, and that should look familiar because over there we have x plus b squared. Well, if this is x plus b, and the whole thing is of course a square, then this should be x, and that should also be plus b there, right? So of course, what's the area of the whole thing? The area is equal to x plus b times x plus b, or you could of course just write x plus b all squared, right? Well, here's the cool thing. This will help us see this as well. If you think about it in all of its pieces, I sliced it that way and that way based on where x and b are separated. Well, how long is this? That's x, right? And then this is also x, and then this mini square here is b by b, isn't it? So another way to find the total area is to split it into its smaller pieces. Well, this biggest piece is just x times x, which is x squared, right? And this piece, his area is b times x, which is bx, so I'm going to have to add that. But this one's the same, it's identical, so that's going to be also bx. And this one's area is b squared. So in the end, I have bx plus bx. In fact, I have this and this. How many of them are there? 2 of them, right? So x squared plus 2bx plus b squared. And this is going to really help us understand the process called completing the square. Finally get to the point where we can solve unfactorable quadratic equations. So completing the square really asks this question, and this is really important, so pay really careful attention to this. How can we form a perfect square? Okay? Let's look back at the visual just really quickly, because I want you to look at something. I've got an incomplete square, right? It's missing this little square in the corner. What I have right now is, I have x squared, and then I have, remember that this is 4 and that's x, right? So I have 4x and another 4x. So what I have is x squared plus 8x. Does that make sense? Now, if I was trying to actually solve an equation based on this guy, and it was equal 0, let's say, you and I both know for this one, actually the easiest way is to factor out x, and then we'd be good to go. But let's just use this method here. You can tell me right now, exactly how much would the area be of this thing if we wanted to fill in this gap? Well, we know it'd have to be what by what? 4 by 4, so I would need 16. Does that make sense? So if I started with x squared plus 8x, what I would do is, to use this method, I'd fill in the square. That's why it's called completing the square. But if I add 16 there, I need to add 16 on the other side as well, right? And then what I get here is a perfect square. I made this a perfect square, because now look, this full square is simply x plus 4 times x plus 4. So x plus 4 squared equals 16, right? And now we can do the backtracking like we said. We can do the square root, and then we can subtract 4. So I get x plus 4 equals plus or minus, the square root of 16 is also 4. And so I get x equals, remember I can subtract this 4. Negative 4 plus or minus 4. And of course, that's going to give me negative 4 plus 4 is 0, and negative 4 minus 4 is negative 8. So 0 or negative 8 would be the two solutions. Now, that seems long and annoying, right? Because you guys probably realize I could have done x squared plus 8x equals 0 and pull out the x times x plus 8, and then I can just see, yeah, 0 or negative 8 without all that work. But we're going to be looking at equations now that, well, it's not just a simple one like this. Maybe it has another number there. It's not factorable, and so it's helpful to make it into a perfect square, and then we can put it in the form that we can backtrack. Our next example, I really would like us to get good practice figuring out what we need at the end to make something into a perfect square, because then we'll really be able to solve equations using completing the square really well. Okay, so I'll remind you of this pattern that we already looked at. We've seen if I start with x plus b and I square it, then I get x squared plus, 2bx plus b squared, right? And let's just not forget the relationship here, okay? Whatever is here is twice that. So if I want to know what goes here, I need to go backwards. I would take half of that, right? And then also whatever's in here ends up being squared. So I actually like to think about it like this. If I want to know what goes on the end here, I can take half of this, which in this case is b, and then square it. That's just how I think about this. So let's do a together here in number 4. It says find the value of c that completes the square, and then factor the quadratic. So first of all, we need to figure out what goes here to make it a perfect square. Well, let's do what I said. Remember, this, whatever half of that is, in this case is 7, and then I square that. Well, 7 squared is 49. Aha! So x squared plus 14x plus 49 is going to be a perfect square. So 49 is the value of c that I need. And it says to factor it also. Well, the factorization of that then is going to be x plus something squared, right? But remember, that's always half. So that's going to be 7. So that's all it is. Okay? So we'll do part B, and then I'll just ask that you do the rest yourself, and we'll give you the answers. So part B, same deal. The only thing here is, this is a negative, but it's still got 14. So again, if we do half, we get negative 7, and then if I square that, I actually still get positive 49. So what's the difference going to be in the factorization? Well, whatever goes here is the half, right? So it's, instead of x plus 7 squared, it's x minus 7 squared. And both of those give me that plus 49 in the end, right? So go ahead and do the remaining of these yourself. Okay, then we'll be done with this section and we'll move on to our next section of video with solving equations. All right, so here's what you should get for this one. Half of 10 is 5, squared is 25. And so this is going to equal x plus 5 squared. Forgot my equal signs. And for this guy right here, if I do half, I get negative 9, and squared gives me plus 81. And then that's going to be x minus 9 squared. This and this, that's weird because they're odd numbers, huh? So it's going to be a little bit tricky. It may be helpful to have your calculator handy. But again, half of this is 5.5. And 5.5 squared is 30.25, so plus 30.25. And then if I break that apart, now when we say factor, we usually mean integers, but in this case, we're going to allow for it to not be an integer. And this is x plus 5.5 squared, if I factor it. And the same thing goes here. We're going to do our half. Half of 23 is 11.5, negative 11.5. And squared is going to be 132.25. And this is then going to factor to x plus, minus 11.5 all squared. So if you have down how to actually complete a square and turn it into a perfect square, then we're ready to solve the equations.